So now we are going to discuss how hydrocarbons are categorized based off of the type of bonds that they have. So we just briefly touched on how there are alkanes, alkenes, alkynes, and aromatic hydrocarbons. So now we're going to learn a little bit more about each of those. Besides aromatic, those, like I said, are a little bit more complicated, but we will learn about the first three. So alkanes. This is whenever you have carbons that are all sp3 hybridized, have tetrahedral geometry, and have 109.5 degree bond angles. So overall, the main idea that you should, the thing that should pop to your head when you hear, okay, this compound is an alkane, you should think alkane, okay, single bonds. And when they are in a straight chain form, meaning they're not like a cycle or anything, a circle, then they will be connected, all the carbons will be connected through a continuous chain. So if you had like a long chain of carbons, right, this would be considered a straight chain form. Obviously, I haven't drawn in the hydrogen, so don't forget about that. But this is what we mean by straight chain form. Apparently, I can't speak today. So remember, always, carbon can make 4 bonds. So because of this, it can have this chain-like structure that it forms, but it can also form branches. So here, for example, and I'm just drawing the backbone of this compound, for example. I'm not drawing the actual, I'm not filling in all the carbons, right? So, don't come for me on that, but just to save space and time. So this is showing you how, we can branch it out, right? So we can draw a little branch over here. You can go any which way, and it can be considered a branch. So there's something about, and it's not something, it's just the geometry of it. The fact that carbon can form those 4 bonds really allows it to have so much variety, where it can form a chain, form branches, it can form circles, so many different things. So that's why we have so many different organic molecules that exist, and that's why this is its own subject in itself. So another phenomena that happens, or something that happens because of these different connectivities that you can have between carbon compounds, you can have the same molecular formula but different connections, and these are called structural isomers. One thing before we move on, I do want to note that because we have all single bonds, and I'm going to clean this up so you can see this better, because we have all single bonds in alkanes, we have the possibility for bond rotation. So in single bonds, you have the possibility for the bonds to rotate. So you see how in this picture, this is showing after a rotation occurs, and you can see how the positions and the shadow of it is slightly different in comparison to this. So single bonds, you can rotate. This is just showing how the orbitals actually look. This is showing the bond angle. Okay, so let's look at some structural isomers that we just mentioned. So some of the formulas of molecules can have chains or branches, right? So you can have like a straight chain type molecule, or you can have one with branches. So let's look at butane, and this is just straight chain butane, like all the carbons are just straight down, right, from each other. And yeah, it forms this long kind of chain-like molecule. And then we have, and this has a special name. The common name that you can call it is called isobutane. The first one was called N-butane. And isobutane, it has the same amount of carbon. So let's highlight how many carbons there are in the top one. There's 1, 2, 3, 4. And if you count out the hydrogens, you'll see that it's also the same, but I'm not going to go through that. So it has 4 carbons. If we count the carbons in isobutane, we see that it's the same. 1, 2, 3, 4. But it's bonded differently. So overall, it looks completely different, right? That looks completely different from this. And then it has a different melting point and a different boiling point. So it has the same formula, but it has a completely different structure. So it has a completely different types of connections that are between the carbons. So you see how here it's a chain, and here you have a 3 carbon chain, and then 1 branching off. So that's what's different about these. So these are isomers of C4H10. They both have 10 hydrogens and 4 carbons. And then we have another example here. This is pentane. So this is C5H12. So again, same situation. We have a chain versus a chain with 1 branch. So they have the same exact formula, but different shapes overall. This is more of like a circle-y type shape with, or like this weird, it has like a bump over here on the top. But this is a big deal. It's it's not like, okay, they're isomers, but overall it's the same. No, so it translates to their overall characteristics. So you can see that the melting points and the boiling points are not the same, so they're completely different because of this. And finally, we have one last example for C5H12. So this is called neopentane. And notice that this is just a carbon with all the carbon groups like attached to this one singular carbon. So it's like this giant ball of these carbons, right? And it's completely different, again, completely different melting points, boiling points compared to the previous 2 isomers. So how do we name organic compounds? So there's a systematic approach for this. We have 3 parts for a compound name. We have the base, which tells me how many carbons are in the longest continuous chain, right? So those chains are important. They help us form our base. So think of how, like, when you make bread, right? There's a base to it. There's a certain type of flour. There's just regular old plain flour. You could also have a base of, I don't know, almond flour that's becoming more popular. So just think of it like that's what's overall giving the main, information about it. And then there's a suffix. The suffix tells you what type of compound it is. By type, we mean alkane, alkene, alkyne, okay? And then there's a prefix which tells you what groups are attached to the chain. So this will tell you what little branches you have or what groups you have. So let's go through this process on naming these compounds. So first, like we said, we are going to find, or like we mentioned, that the most important thing is the chain, right? So we're going to find the longest continuous chain of carbon atoms and use this as our base name. So here we have a chain of 1, 2, and I'm not going to circle all of them, but it goes all the way to 6 carbons, right? Imagine that, I'm new at this. I still don't know what's going on in this class, so I'm just going to find the first chain I can see. So let's say I found this one, and then 2, and then 3. That is a chain of 3. And then let's say for some reason I considered this over here just a branch. This would be incorrect because you can see it's not the longest chain. 3 versus 6 that actually exists is smaller. So you look for the longest chain. Here it is 6. Okay, so we have chain of 6 carbons. Number the chain from the end nearest to the first substituent encountered. So where do you see the first branch or the first group on this chain? So notice if we try to number it this way, 1, 2, 3, 4, 5, and 6, your substituent or your first branch or your first group is on carbon number 5 versus the other way around, which is already pre-written on here. it's on carbon number 2. So that is what is preferred. You want the chain to be numbered so that the first group is encountered the fastest, or like first. Name each substituent. Side chains that are based on alkanes are called alkyl groups. So essentially, we're going to be taking the prefixes that we're going to be learning about, and we are going to be applying it to these groups as well. Okay, so you might have noticed this compound already has a name, right, on it. How did they determine, okay, this is going to be hexane? So we know that there's 3 parts, right, to a name. So let's break down this name that we have here. Methylhexane. So this has 3 parts, even though it may not look like it. There is this part, there is this part, and then there is the ane. The ane is the part that tells you that we have all single bonds. And you can see that there is all single bonds within this compound. This part in the middle, the hex, tells you that there are 6 carbons in the longest chain. So 6 is the, or hex is the prefix for 6 carbons. So here you can see that there are up to 10. So these are all the prefixes for the, after determining how many, whether you have all single bonds or whether you have a double bond within there or a triple bond, that is how you determine what you put in front of the ane, or ine. And then the first part, which is what we're getting to last, is adding in that information about your group. And that goes all the way at the front of the name. So we have 2-methyl. And the 2 right here tells you the position of where this group is on the chain. So it's on carbon number 2 of the longest chain. And then the methyl tells me that I have a group that has a carbon with just 1 in it. Because this could be a longer chain. This could be, you know, for all we know, this. And this would be CH2. So you could have a case where you have an ethyl group instead. But here we only have 1 carbon attached on that long 6 carbon chain. So it's called a methyl. So that's where that comes from. So this is the group. So those are the 3 parts that make up this name. Some more information on these alkyl groups. So that's what I was just mentioning, the methyl. These are specifically called alkyl groups. So you can have methyl, you can have ethyl, propyl, and notice that these are using those same prefixes that we use to describe the base chain as well. So, you know, that's useful because the prefixes mean the same thing. There's no confusion there. You can also have these more bulky and complicated groups like isopropyl, really, really big group like tert-butyl. So those have specific names. If you do take organic chemistry, you will learn more about that. So here we have an even more complicated compound. So notice that, okay, we found the longest chain within it, and that happened to be starting from here all the way to here, and there are 7. So there's 7 carbons in this base chain of all single bonds, so heptane. So that's where that comes from. We know that part. Now what about everything else? So notice that we have several groups, and we started numbering on this bottom end because the first group that pops up is this one right here. And then we have, so that's a methyl group. And then we have an ethyl group right here because it has 2 carbons. And then that's another methyl group. And then this is another methyl group. So you have 3 methyl groups and 1 ethyl group. So how do we take care of that with, you know, the prefix being the groups, right? Not the prefix. At the very beginning of the name, we include the groups, or we specify what groups there are on this compound. So you're going to begin with the name with the numbers on the carbon atoms to which each substituent is bonded, right? We talked about that, how we specify where the number comes from, and how that is where the group is bonded. When two or more substituents are present, list them alphabetically, ignoring the prefix when alphabetizing. So we will be listing them alphabetically. So we have ethyl and methyl. Ethyl, E, comes before M in the alphabet. So that's why we have 3-ethyl. And then we list all the places where the methyls are bonded to, the locations. And it is 2, 4, 5. And you put dashes in between that. So 3-ethyl, -2, 4, 5, try to show that there's 3 methyls, heptane. So you can see how it can get very complicated, and these compounds can get very long, the names. Next we have alkenes. Alkenes are those carbon compounds, those hydrocarbon compounds that contain at least one double bond between two of the carbons. Specifically, this double bond is made up of a sigma and a pi bond. Unlike alkanes, where you have nothing but single bonds, and those single bonds can actually rotate freely, as I mentioned very briefly, there's no free rotation about a double bond. It's stuck the way it is. The naming is a little bit different, where the longest chain must include that double bond between the carbon atoms, and the ending is an "ene" instead. In addition, there's a special type of isomer that exists within alkenes, or because of that special characteristic of alkenes, where there is no free rotation about that double bond. So what you end up having is you can have these two different types of isomers, cis and trans isomers. And I'm going to show you an example. So here we have two sets of isomers. We have, for example, this one. This is actually, okay, so this is showing the naming. I got confused there for a second, and this is showing isomers. Okay, so here, this set of isomers, we have cis and trans. The cis isomer will have the groups on the same side. By side, we mean splitting that double bond down the middle and looking at where these groups are. So on this isomer, we have both of those groups on the same side. On this isomer, we have them on opposite sides, so it's called the trans. So these are geometric isomers where the positioning of these bonds is different, and they're essentially stuck like that. These can't rotate, so that you end up having this on the other side, right? So they're stuck like that. So that's why, they're permanently isomers to each other. And it does translate in the same way that structural isomers, the differences translate to their physical properties. You do have that same situation. So here the BP is +4, here the BP is only +1. Here this is showing you the naming and how you have to have the chain include your double bond. Finally, we have alkynes, and this is whenever you have a triple bond between a carbon. Specifically, you have a sigma and 2 pi bonds within that triple bond. This is considered unsaturated, and the naming, similar to alkenes, you have to include the carbon in the triple bond, and you have to end it in "-ine" instead.